Welcome to the Unit 10 guided practice. Let's start by talking about acid-base definition. It says, how does the definition of a base change when considering a Lewis base, Bronston-Lowry base, and an Arrhenius base? When we look at these, we're really looking at what particle defines each definition. So in an Arrhenius, the base is defined by having a hydroxide ion attached to it. In a Bronston-Lowry, a base is defined by protons. So does it donate a proton or accept a proton? And we know that acids are going to donate a proton, so a Bronston-Lowry base is going to accept that proton. And then a Lewis base. A Lewis base is defined by the giving or accepting of electrons. And so we know that the Bronson or the Lewis base is going to donate an electron. And so it's really defined by the subatomic particle or the ion attached to it. It says write an expression showing how that hydrogen iodine, or we would say our hydroidoic acid, meets the definition of an acid. And so when we're looking at this, we want to look at each definition. And so the Arrhenius definition is showing by it donates a hydrogen ion. And so we would say Hi is reacting with water, or actually it's just reacting, and we can show it going into a hydrogen ion and an iodine ion. And since it donated this, we would say that it's Arrhenius. Bronston-Lowry would say because it reacts with water, we say that it donates a proton. And so the iodine ion is formed, and then the water accepts it, and so the water is considered a base here, and it turns into our hydronium ion concentrate, or hydronium ion. And then lastly, with our Lewis, what we would say is drawing the Lewis dot structures. We would draw it with the bonds already here, and water with its electron bonds and its lone pairs on top and its hydrogen. And what we would say is that it's considered an acid because it accepts an electron. And so iodine would accept an electron and become negative, and our water would donate an electron and create our hydronium with our hydrogens attached to it. And so really we're looking at it because defined by the movement of the electron. See, it says what determines if an acid base can be classified as weak or strong. Strong means that it ionizes completely, and weak means that it only partially ionizes. So if it only gave up a little bit of protons and not all of it, then we say it's weak. If it donates every single proton it can, then it is strong. Make a list of strong acids and strong bases. Some strong acids would be our perchloric acid, our hydrochloric acid, our hydrobromic acid, hydroidoic acid, our nitric acid, and our sulfuric acid. Some strong bases are going to be our lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. And it says E, draw a diagram illustrating the specificity of the three definitions. So when we look at this, we know that all Lewis acids, they cover every acid that there is. It's a broad definition that covers all of them. So that's Lewis. The Bronston-Lowry definition covers the majority of acids, but not all acids. And then lastly, Arrhenius acids only cover acids that have a hydrogen to donate. And so basically we can say this, that all Arrhenius acids are Bronston-Lowry acids and Lewis acids. Some acids are only Bronston-Lowry and Lewis. And some acids are just Lewis acids. They can only be defined by that. And so Lewis covers everything. Bronson Lowry, the majority of things, especially in the class we're talking about. And then Arrhenius covers a smaller amount of acids. Looking at naming acids and bases. When we name acids and bases, bases are simple. They're going to name using just our formal ionic compound naming. So you name the metal, check if it's D block, and then it's going to have a hydroxide on the end of it. So like our first one, we have barium and we have hydroxide. Since barium is not in D block, it only has one oxidative state. It's just barium hydroxide. Here we have iron hydroxide. Since iron has multiple oxidative states, we need to know its oxidation number. And so since we have two hydroxide ions and hydroxide has a -1 charge, so that means the overall charge contributed by hydroxide is -2. That means we need a +2 from iron to balance it out because all ionic compounds are neutral. So this would be called iron 2 hydroxide. Now with acids, when we're dealing with it, we're looking and we're naming it according to the polyatomic ion. So on our first one, we see that what's attached to it, or its ion attached to it, is going to be, our anion is sulfide. And so since it ends in IDE, we would say that this is hydrosulfuric and then acid. The next, since the ion or the anion is going to be chlorate, since it ends in ate, all we do is add an ic ending. So this is chloric acid. And if it was an ite ending, so say this was HClO2, this ended in ite, it would just be chlorus acid. So if it ends in ide, we put hydroic. If it ends in ate, it's just ic. If it ends in ite, it's us, and then acid. So here it says write the chemical formula for the acid and the base below. So we have lithium hydroxide. So we have lithium +1 charge, hydroxide -1 charge, you crisscross and you get LiOH. So you just bring that one down, and we don't put ones. Next we have tin 4 hydroxide. So tin is SN, has a +4 charge. Hydroxide is OH -1. Bring down that 1, bring down that 4. We get SN. It's not one to write there, but it's SN. There we go. OH4. Nitric acid. So nitric, since it's IC ending, that means it's hydrogen bonded to nitrate. So just HNO3. And then hydroic. So we know that it's hydrogen bonded to an element, which is phosphorus. So hydrogen has a +1, phosphorus is -3, so this is H3P. Moving on to pH and POH calculations, it says a 2 milliliter solution of a 0.25 molar hydrobromic acid is added to 100 milliliters of a 6 times 10 to the -3 molar sodium hydroxide. And so what is the resulting pH? So it's strong acid, strong base. And so initially you can think and look of this and write the reaction. So what you're going to have is you're going to have your hydrobromic acid plus our sodium hydroxide, so our NaOH, and it will make those ions and water. Okay, so it neutralizes. The neutralization reaction creates this. So in the very beginning of this, you got to look at, well, how many moles do we have of each substance, and we can work from here. So all you do is multiply the volume times the molarity, so 20 times our 0.25, and we get 5 millimoles of our hydrobromic acid, and then 100 milliliters times our 6 times 10 to the negative third, and we get a 0.6 millimoles. Now, when they react, all of this sodium hydroxide, since it's in the lower quantity, will get used up. So this will go down by 0.6. This will go down by 0.6. This will go up by the same amount, and up by the same amount. Now what we care about is the only thing in solution contributing to the pH now, so add everything up. This is 0, this stays the same, and this goes to 4.4. This is the amount of moles of our hydrobromic acid that we have. Since it's a strong acid, that's how many moles of the hydrogen ion we have in solution. And so we have 4.4 millimoles of this in, we put 100 milliliters with 20 milliliters and 120 milliliters of solution. Remember, because this is millimoles, we have a concentration of 0.0367 concentration of our hydrogen ions, and we just take the negative log of that because that's what pH is, and we get a pH of 1.44, which should make sense. That's acidic, and what we had left over was an acid. Next, it says a 50 milliliter solution of our perchloric acid with unknown concentration is titrated with a 0.15 molar lithium hydroxide. The resulting solution turns pink at 37.2 milliliters. What is the concentration of the original solution? So when we're looking at this, since it turned pink, that means it reached the equivalence point. So it has equal molar amounts at this point. So if we take our 0.15 times our 37.2 milliliters, that is going to give us a millimole concentration, which this means that the same millimole concentration that our acid started with, because that's what the equivalence point means, that you're at the equivalence point and you have the same molar amounts, which means we have 5.58 millimoles of our acid, and it's in 50 milliliters. And so what we get is we get a concentration of our acid of 0.112 molar solution of our perchloric acid. Next, it says what is the concentration of our hydrogen ions in solution with a pH of 3.2. So pH equals the negative log of our hydrogen ion concentrations, or hydronium ion concentrations. So we're solving for that, and so we have 3.2 equals negative log. And remember, you have to do the opposite of our function, and we're going to get 10 raised to the negative 3.2 equaling our hydrogen ion concentration, which when we do this, we get a concentration of 6.3 times 10 to the negative fourth molarity of our hydrogen ion concentration. Now, looking at weak acid calculations. So it's weak acid, so not all of it's going to ionize. It says calculate the pH of a solution of a 0.35 molar of our weak acid. It's just an unknown weak acid. Has a Ka value of 4.8 times 10 to the negative fourth. So we want to know the concentration of it. So first thing we have to do is write the equilibrium expression, and so HA is going to dissociate into hydrogen ions and an anion, and this means we have a Ka value of our hydrogen ion concentration times our anion concentration all over our acid concentration, and this is our Ka value here. And so when we look at this, we think of our expression and how it's written. Here's our equation. From this equation, we start out with 0.35 molar of our acid, and then it's going to go down. It's going to change by X and X. So those guys, when it disassociates, H and A minus are going to go up, and this guy's going to go down. And at equilibrium, we'll have 0.35 molar minus X, and these guys will be X and X. And we plug these values into our expression. Now the one thing we say, since our Ka value is 4.8 times 10 to the negative fourth, it's so small that the minus X is going to be negligible, so we really don't need it. So our Ka expression is going to look like X times X all over 0.35. Plug in your Ka number there and solve for X, and X is going to give us a concentration of 0.013 for our X, which that X is our hydrogen concentration. We take the negative log of that and we would get a pH of 1.89 for our pH. Go ahead, and on B it says write the equilibrium expression showing cyanic acid as a weak acid. It should be hydrocyanic acid. And so when we do this, we would take our HCN, breaking it up into H plus CN minus. Remember that our Ka expression is products over reactants, so these guys over that guy. And lastly, it says write the equation demonstrating acetic acid is a weak acid. What you should get is you should get Ka equals H plus C2H3O2 minus all over the concentration of HC2H3O2. See if you can write the equation and see how I got that. Next, it says, what is the oxidation number of all the elements in the following? When the elements are by itself, they have an oxidation number of 0. This is the elemental form of chlorine. It's not by itself, but it's its elemental form, and so that also has an oxidation number of 0. When we look at an ionic compound, we know that the anion is going to stay what it is on the periodic table. So chlorine normally has a -1 oxidation number. Since there is 2 chlorines, that means that overall chlorine has a -2 charge. And if the whole molecule, the whole atom, or sorry, whole compound wants to be neutral, if chlorine is -2, then calcium has to be +2. Looking at an ion, we have our ammonium there, and what we see is we have our hydrogen, which our hydrogen is going to be a positive charge, and there's 4 of them, but the overall charge is going to be positive. So when we look at it, the overall charge needs to be +1. Hydrogen is +4, so what added to 4 plus 4 is going to give us +1. And so what we get is +1 equals +4 minus 3. All we have to do is just subtract 4 from both sides, and we find out that X is -3. So nitrogen is -3, hydrogen is going to be +1. It says write the redox reaction half reactions for the equation below. They're separated and put in 2 beakers connected with a wire, so they created a galvanic cell. Now what we look at is we have to look at change in oxidative states. So zinc is going to be 0, and this should be ZnCl2. This is 0. Hydrogen is +1, and we know that chlorine is going to be -1. When they change, now hydrogen is 0, zinc is going to be +2, and chlorine's -1. And so what we see is that zinc went from a solid to a +2 charge, and so therefore it had to give up 2 electrons. Hydrogen went from a +1 charge, it gained an electron and made H2. Now to do this, that means we have to balance it. So two hydrogens and two electrons had to do this, and we get our oxidative reduction half reactions. And it says B says redox reactions are governed by the law of conservation of charge. And so we see here that if our hydrogen gained two electrons, then our zinc had to give up those two electrons. And what does redox stand for? Redox stands for reduction and oxidation. So oxidation reduction reactions are redox reactions.